Woohoo! Welcome to 9.6, the chain rule and the power rule. Now, before we get into this application or technique of differentiation, I want to review a little bit. I want to review a concept called a composite function. So, recall from chapter 1 that we can create a composite function from two other functions by substituting one function into another. And it's a little bit hard to see, but there's a little open circle there. And sometimes I used to call it fog. It's pronounced f of g of x. F of g of x. And what happens is we're going to take g of x first. So we plug in whatever x is going to be into g, and then we take that whole package and stick it into f. And what we generally want to do is, if we can, rather than having to go through all the steps each time, let's go ahead and come up with a single expression for this new composite function. So it's kind of like a Franken function, and I don't have any Franken monsters, unfortunately. Oh well. So I've got f of g of x, and I know what f of x is. F of x is going to be x squared plus 1, and g of x is going to be 3x minus 2. So far, so good? Woohoo! So the first trick is to recognize that we're taking f of g of x. So we want to take f of whatever g is. And since I've been using blue right there, I'm going to go ahead and put blue right here. Okay, so whatever goes inside of f, what is the rule for f? The rule for f is that we've got f of x equals x squared plus 1. So that means that this box is going to come out, we're going to square it, and we're going to add 1. So far, so good? So what we want is we want f of g of x. That's that blue box right there. That g of x is the blue box. So that's going to be g of x, right? Because that's the blue box, squared plus 1. So far, so good? So we're going to take g of x, we're going to square it, and we're going to add 1. Okay, so I've squished myself into a corner here, so I'm going to go ahead and do a swoop-dee-doop-dee and come back over here and give us a little bit more space. So we've got g of x, that squared, plus 1. Well, g of x right there is 3x minus 2, right? We know what g of x does. It says take 3 times x minus 2. So we're going to square that and add 1. And I know everyone's like, oh, do we have to square it? And the answer is, well, yes, unless you've memorized the formula. So there are a couple things you can do. You can memorize the square for the formula for a square of a binomial, which I'm sure you've all done, but just pretending you didn't. You could also go ahead and just FOIL the heck out of it. Don't forget the plus 1. We have to add 1 when everything's done. So let's see. If I FOIL this, I get 3x times 3x, and then outer minus 3x times 2, inner minus 2 times 3x, and then last, negative 2 times negative 2, that gives me a positive. So I think I get, oh, what did I leave off? I got so excited I left one thing off. You got it, the plus 1. Okay, so I've got 9x squared minus 6x minus 6x plus 4 plus 1. And that's going to give me, oh my goodness, 9x squared minus, combine those two, 12x plus 5. What do you guys think about that? Woohoo! So what is that again? That is f of g of x is equal to 9x squared minus 12x plus 5. And so what we've done is we've found the composite, right? Composite is a word that means you take some stuff, in this case two stuff, and stick them together, right? So we've got that all stuck together. So we've got the composite function. Now, what we would like to do is to find the derivative. Okay. So let me kind of squish this up a little bit. Sorry about that, Godzilla. Okay. So find the first derivative of f of g of x. Now, this gets really complicated, so I'm going to use, remember there are multiple notations for derivatives. I'm going to use this one. The derivative with respect to x of the composite function f of g of x, which I could also write as f and little o g, right, the fog, okay, is the derivative of 9x squared minus 12x plus 5. Okay, so what is the derivative now at this point? This part was the hard part, the composite function, taking the derivative. Easy peasy, right? Bring the 2 down, so it's 2 times 9, x to the 2 minus 1. Negative 12x becomes a negative 12, and the plus 5 disappears, right? It's 0. So I think I get 18x minus 12. Woohoo! So, the question at the bottom is not, why are we doing this? Although that is a fair question too. But this is something that comes up a lot. If you've got a composite function, is there a way to get to this derivative without having to go through this mess? Do we have to find the composite function and then take the derivative, or is there a shortcut? And the reason for that is because derivatives are easy. Once you know the formula, they go really fast. Finding composite functions, frequently very long, and in fact, sometimes it's, harder than that. So is there a way to do it? And if I said no, let's move on, that would be a very short chapter. But in fact, sorry about that. Dun 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 dun! There is! Woohoo! Yay! The chain rule. Oh, it's too bad that I already swore that I would never sing again, because I really want to sing that song, but I'm not going to sing that song. So here we go. Me not singing. If f and g are differentiable functions, so in other words, you can take derivatives of them, right? So that's basically, if you're allowed to take derivatives, then we can play with those functions. And then the world gets weird with y equals f of u and u equals g of x. Oh my goodness, what happened? Why is there even a u here? And the answer is, believe it or not, this is an attempt to make this easier to understand, which I know a lot of people are thinking, what the what? That's not easier to understand. Suddenly there's a u. So if I've got y equals f of u, and then u equals g of x, u is just g of x. So this is just a fancy way of describing the two parts of a composite function. So we've put the one function on the inside, this is g of x, and f of x goes around it. Then the chain rule says, dun 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 dun, the derivative of y with respect to x, so the derivative of the whole thing, is the following. The derivative of f with u, what is u? G of x. So the derivative of f of g of x and the derivative of g. And now you're saying to me, seriously, can we just go back to page 1? And the answer is, well, you could. In a lot of cases, doing all of this mess that we did on the first page, yes, totally doable. In some cases, though, not doable at all. So it really depends on the situation. So sometimes you can just do it the long way. But why is the short way good? Well, so it's going to take a couple of examples, and I've got a couple of examples to show you including this first one that we're going to do, then a couple more in the next video. But once you get the hang of it, you'll notice that you don't have to use plain f anywhere. This is the derivative of f. Remember, derivatives almost always simplify things, right? So a simplified version, we hope, and a simplified version of g. So the goal is you're going to do a little bit less work. So I know this is, again, that central riddle to math, which is, so we're going to do a bunch of work so that in the long run, we can do it with less work. And the answer is yes. It's like a work investment scheme. You invest the work now, and then you do less work later on. That's the goal. Now, here is a really interesting one, and it's tantalizing because it suggests a lot of people, and I don't even want to touch my pen, but a lot of people will notice this looks a lot like fractions, and like you could just cancel the du's and you could see the dy on top and the dx on the bottom. And I'm not going to say that that is entirely wrong, but it's not where we're going right now. Because what we want to do is we want to look at the derivative of y with respect to u, and then the derivative of u with respect to x. Okay, that's a lot of theory, and you're all saying, yeah, sure, this is going to get easier. Well, let's give it a try, see what you think. So, the better way to remember it, in my mind, take the derivative of the outside, and then the inside, but do it separately. So what does that mean? So, you'll recognize same functions we had before. If I have f of x, and that's x squared plus 1, then the first thing we're going to do is we're going to find the derivative of f of x. Okay? And again, in this case, it does get much simpler. It's 2x. Nice. Okay. And if we have g of x, that's our other function, 3x minus 2, then I know what the derivative of g is, right? The derivative of 3x minus 2 is just 3. In this case, and this is why I picked this one, you can clearly see the derivatives much simpler than the original functions. So you can kind of already anticipate, okay, this is going to simplify some of our calculations a bit. So now, how the heck do we use all of this? Because we're going to need all 4 of these. So what are the pieces of this? So I'm going to write this out. It said dy dx equals f prime of u and g prime of x. And remember that u is just g of x. Okay? So, f prime of u. Remember when we did functions way back in the beginning and I had you practice plugging other variables in and you're like, why would we ever have to do that? This is what we're going to do. If f prime of x is 2x, then f prime of u, we write it up here, so maybe it's up here. F prime of x is 2x, so f prime of u is 2u. Okay. There we go. What's g prime of x? That's 3. And in fact, since this page is looking very black and white, let me do some underlining. There's our g prime of x. And here is our f prime of u right there. Okay. And then 2u times 3, that's just 6u, right? Now, the problem is the problem wasn't in terms of u, it was terms of x. So what is u? U is g of x. Let me get one more color going here. U is g of x. It almost sounds like kids on a playground. No, u is g of x. So u is g of x. So 6 times u is 6 times g of x, right? Because that's u is g of x. There we go. And then I know what g of x is, right? G of x is 3x minus 2. So that's 18x minus 12. Okay. Drum roll, please. Same answer. We got exactly the same answer on the front page. So, the big question for you is, well, was this easier than this? And I would claim that this was harder algebra, but this requires a lot of remembering a formula. So really, we're in a situation where you would get to choose. Hopefully, though, I've made my case that the actual algebra here is so much simpler. You don't have to square anything. And so that's one of the benefits of the chain rule, is that sometimes you want to take a derivative, but you don't want to square anything. And this gets you out of squaring something. Or, I mean, really, cubing something. Ugh, there's some yucky stuff you got to do. So this kind of saves you a step. That's the goal. So this is the end of the first video. I'm going to go ahead and continue. I've got a few more examples, and then we're going to talk about a related technique that's related to the chain rule. And so we'll do a couple examples of that in the next video. Woohoo! You guys are awesome. Congratulations. You made it through yet another video packed full of math. So you guys are awesome. Go out, be nice to yourselves. Look at something green. Change your focus. Maybe get something nice to eat. Get a drink. Maybe curl up in a blanket and read your favorite math book, or another book. I'm sure there are other books in the world. I mean, I don't know why anyone would read them, but, I'm sure there are other books. But math or otherwise, give yourself a break and congratulate yourself because you're awesome and amazing. And math on. Woohoo.